Hello there, welcome back to Life Lessons for Math. As always, I'm your host Wesley, and today I'll be diving into part 3 of my Introduction to Calculus series, and we'll talk about integrals, which are a pretty integral part of the research process, and just math in general. Sorry, that's a terrible pun, but I did warn you that I love puns, so... Cool, so in the past 2 videos I've talked about limits, which are the building block of calculus and just analysis in general, and derivatives, which allow us to find the slopes of tangent lines, and in turn those tangent lines allow us to take nonlinear problems and make them linear, which are much more straightforward and usually easier to solve. With that being said, today we'll be talking about integrals, and the motivating question is, what is the area under a curve? And like I said in last week's video, it's the second of the 2 questions that motivated the discovery of calculus. Okay, so what is an integral? Well, basically, kind of like a derivative, it's the answer to this question. An integral is a tool we use to find the area under a curve. Cool, but why? Well, it turns out that integrals, kind of naturally pop up everywhere, just in like physics, chemistry, biology, geology, like just the sciences. Integrals pop up everywhere, and in fact most partial differential equations begin their life as an integral, and then they're usually reduced down to a PDE. And so integral equations are usually just what nature naturally produces. That's just the rules that govern it, and so that's why integrals are so integral. And in fact, integrals are what we use usually to solve PDEs in most modern research. Okay, with that being said, integrals do more than just help us find the area under a curve. They also help us to find the arc length, so the length of some wavy shape. They can help us to find the surface area of some 3-dimensional object, the volume of 3-dimensional objects, the flux of an object. So let's say you have a net and you put it in a river. How much water is passing through that net? You can use that using integrals. They can help you find work. Just all sorts of physical applications are present with integrals. And they can, for me, one of the big things I use integrals for are for average values, and to kind of weaken the notion of a derivative, which we'll do that in a future video, talking about weak derivatives. But again, mainly for average values. So I'll talk about that today. With that being said, I have a couple more things to talk about just to kind of motivate the life lesson for today. So it turns out that integrals and derivatives are actually very related to each other. So that seems kind of weird at first glance, of like, the area under a curve is related to the slope of a tangent line? Like, what? Why in the world would area be related to the slope of a tangent line? Good question. And so that's something known as the Fundamental Theorem of calculus. Basically, in math, a fundamental theorem relates 2 unrelated areas and says, no, those things you think are unrelated are actually very intimately connected to each other. And my life lesson for you today is to think about, well, what fundamental theorems are present in your life? What, are aspects of yourself that you tend to put in boxes and say, like, those 2 things aren't related to each other, but actually are very, very related to each other because we're not linear creatures. What happens in the morning affects what happens Monday morning can affect what you feel Thursday night. Those things we're very connected creatures, and we tend to ignore that fact a lot of the times. So that's going to be my life lesson for you today. With that being said, I want to talk about integrals and how they help us find the area under a curve. And really, how they help us do that is through something known as a Riemann sum approximations. Basically, the idea is that a Riemann sum approximation is like, well, finding the area of something that's curvy and wavy is really hard. So let's use the easiest thing we know how to find the area of, a rectangle, right? If we have a rectangle with length and width, We know the area of that is just, well, the length times the width. They're very easy mathematically to compute the area of. And so we're going to use rectangles to approximate the area under our curvy thing, and then we'll use limits to actually find the exact area. So that's the big picture idea. So how does this work? Okay, good question. Thanks for asking. Let's say we're looking at our favorite function, y equals f of x, and we want to know the area of our favorite function from our favorite number to our second favorite number, b. Okay, so we're looking for the area under this curve, right? We want to figure out how much that area is, and well, what we're going to do is use rectangles. So let's say we want to use 4 rectangles to approximate this area. Basically what we're going to do is we're going to split it up into 4 sections. So that's 1. So we're going to call the endpoints here x0 and x1 to denote our first rectangle. We'll have our second rectangle. Actually, I don't want to put the height on it quite yet. But we'll have our second rectangle, let's say at x2. Let's say that our third rectangle is pretty thin, and then we'll have just kind of our fourth rectangle come from our endpoint B there. Okay. Cool, so we have our 4 intervals that we split it up into, right? 1, 2, 3, 4. And just to go ahead and find the widths, or the lengths, depending on how you arrange it, but I'm going to basically call this the width and this the height of our rectangle. So our width is going to be delta xi, where I is going to be 1, 2, 3, or 4, denoting either our first rectangle, our second rectangle, third rectangle, or our fourth rectangle. And so I just corresponds, I can be 1 to 4, again, corresponding to that rectangle. And how we calculate that is we look at the right endpoint minus the left endpoint. So for instance, the width of our first rectangle is x1 minus x0. So at I equals 1, that's what we would get out. And that tells us the width of our first rectangle. Cool. So how do we find the heights of our rectangles? Well, to find the heights, we just pick some random value between x0 and x1. And we're going to call that value t1 for our first test point. So for instance, I'll use black just to kind of make it stand out a little bit. Let's say our first test point is right here. Well, so that'll tell us what the height of our rectangle is. So we go up to our function value there, and we're going to use that as the height of our rectangle. And so we calculate that by just plugging our test point in. And so that tells us the height. We have our width. And so now we can start calculating our area, right? So it's our height times our width. So that's the area of our first rectangle. Then we do the same thing with our second. So let's say our second one is over here. So we draw that up. We create our rectangle. And so we would get plus f of t2 delta x2. And then you do the same thing for the third rectangle and fourth rectangle. So you'd get f of t3 delta x3 plus f of t4 delta x4. All right, where t3 and t4 again are just our test points, and so we can actually have them line up with, you know, x2 or x3. It could be one of the endpoints. It doesn't have to be though. And again, the rectangles can all be of different length. So let's say that's what we got going on. Cool. So yay, we get a Riemann sum approximation with 4 rectangles of our area. But notice this isn't necessarily a very good approximation because we didn't include that area or that area, and we have that area added in, so there's some under approximation, some over approximation, so it's not a very good approximation. So we're going to try to make that better by basically adding more rectangles. The more rectangles you have, the less room for error there is when finding the approximation. So before we find the extra rectangles, what we're going to do is we're going to introduce some new notation, which I guess you could call mutation. Anyways, this little 3 looking thing here, backwards 3 looking type thing, is a Greek letter sigma, and in particular the capital Greek letter sigma, and basically that is just a notation we use for adding stuff up. And basically what it says is, here let me go ahead and finish writing out the notation, is it says you plug in I equals 1, so we would have f of t1 delta x1, and then you plug in I equals 2, so f of t2 x2, then plug in 3, plug in 4. And then you start wherever it tells you to, stop where it tells you to, and so this is just a compact way of writing this out. Right. Cool. So in order to add more rectangles in, again, I just want to motivate that this really does give us a better approximation. So let's say we're looking at our same function from our same favorite number a to our same favorite number b. And I'm just kind of mixing the colors up just to help maybe add some clarity. So again, when we add more rectangles in, there's less room for error. We have a much more accurate thing. You know, notice none of the errors are nearly as big as that error there. Oh, excuse me. And so what we're going to do is we're going to formalize that idea of like, okay, if we could just have an infinite number of rectangles there, we would have the exact area. And so how do we do that? We do that with a limit. So what, you know, there's a couple different ways to write this down. One is to basically, hey, just say, require that the number of rectangles goes to infinity and that the widths go to 0. Basically, I'll write that as the limit as n goes to infinity, and then I'm just going to kind of put in parentheses here, I'm going to require that the widths go to 0. This notation just says, hey, I want the width of my rectangles to go to 0 so that, you know, I really do have as many rectangles in there as I can, because basically as the rectangles get smaller and smaller, I need more and more rectangles to fill it up. And so, again, I'm writing it as n goes to infinity, but you could also write it with the width going to 0 there. And so we're looking at the sum from 1 to n. So instead of 4 rectangles, we could have n rectangles. Again, our heights at our test points times the widths of our rectangles. And boom, that's how we define the area under a curve. But just like with the derivative, right? Last week we talked about how we defined the derivative using the limit of the slopes of secant lines. Rather than use the area as the limit of the sums of areas of rectangles, we're going to instead use an integral to do this. So basically what we do is, this is kind of a two-step process, is we define the integral from a to b. So this little s-looking thing here is called an integral sign, and it looks like an s for a reason. It comes from Leibniz's notation, and basically he chose an s because you're summing stuff up. It's like, oh, we sum stuff up, so let's just call the integral, or use an s for the integral. So it says, hey, the integral from a to b of my original function in the x direction. So again, this notation here, this dx, says I want to find the area in the x variable, or if there were multiple variables going on, you could say I want to find the area in the y direction or the z direction, etc. Right? So it says the area from a to b of under the curve f in the x direction is given here. Cool, so this is how we define an integral originally. We just defined the integral to be the area, and the area is defined to be this limit. So this is our integral. But this limit definition is incredibly unwieldy. I mean, it's just really difficult to actually use on the ground level, you know, in the field, so to speak. When you want to get your hands dirty and actually calculate some areas, it's not very useful. it is still useful in research level mathematics. One of my friends actually loves using this Riemann sum definition of integrals to find areas under curves. But again, outside of research level mathematics, it has very little practical use. So with that being said, how do we actually calculate an integral? Well, we do that with something known as the Fundamental Theorem of calculus that I mentioned earlier. Let's see. And basically, not my best handwriting there, sorry. The fundamental theorem of calculus goes as follows. It says, if capital F is an antiderivative, which I'll break down what an antiderivative is in just a second, of little f, then the area, which we define to be the definite integral from a to b of f of x dx, which again is given by that limit definition that I gave on the previous slide. It says rather than use that limit definition, what we can actually do is we can write this as the antiderivative evaluated at our right endpoint minus the antiderivative evaluated at our left endpoint. Cool. So rather than use some unwieldy thing, all we have to do is find the antiderivative, plug in the endpoints, and subtract. That's way easier than using a limit definition. But what is an antiderivative, and why is this the fundamental theorem? Why is this relating tangent lines and areas and all that stuff? Okay. So to motivate what an antiderivative is, I want to give a concrete example. So let's say we're looking at f of x equals x squared. Basically, an antiderivative asks the question, if I treat little f as the slope of a tangent line, what capital F would be my original function? So if this is the slope of my tangent line, what does my original function have to be? It goes backwards, because remember with the derivative, it's like, hey, I have my original function, I take the derivative, I get the slope of my tangent lines. Here I'm saying, well, I'm going to treat this as the slope of tangent lines, what is my original function? So it's that backwards process. And so it turns out that my antiderivative would be 1/3 x cubed, and I'm going to put a caveat, a star on that, an asterisk, and I'll come back to that and clarify what I mean, but just keep that in the back of your mind. I'm going to have to revisit this in just a second. Okay, so I claim this is the antiderivative. With antiderivatives, you can always check your work, because the derivative of the antiderivative, right? So if I take the derivative of my antiderivative, I should always get back to my original function, which makes sense. It's like derivative should undo the antiderivative. And it goes the other way too. If I take the antiderivative of the derivative, I get back to my original function. So these two processes are inverses of each other. They should undo each other. So let's check this. Didn't want to do that quite yet. What is the derivative of my antiderivative here? So I'm going to kind of put question marks around here, because this is the thing we need to check. The derivative of this is, well, basically with a function like this, we have a power rule. So to calculate the derivative, I would bring the 3 down. So I would have 3 divided, so I would multiply 1/3 and 3. So 1/3 times 3 is just 1. So I would just get 1 out times x, and then I would subtract 1 from 3 and get 2. So I would get 1x squared, which is my original function. So yay, this really is an antiderivative. But notice if I add any constant, this is still an antiderivative, because the slope of a tangent line to a constant function is always 0. Constants always have 0 slope. And so because they always have 0 slope, when I take the derivative, when I calculate that slope, it's just 0. And so 1x squared plus 0 is still x squared, so this is in fact still an antiderivative of that. So basically, antiderivatives, you can pick whatever constant you want. And so, in general, we just pick our favorite number C, or maybe our third favorite number, since we already have two favorite numbers going around. We pick our third favorite number C, we slap it on there and be like, hey, there's our antiderivative. But there are cases called initial value problems where you would actually solve for C. And that's that basic idea of an initial value problem is actually very important to PDEs, to that research. So, cool. Does that make sense as to what an antiderivative is? It's the function that you need to take the derivative of to get your original function. Cool. And notice, again, in all this, I was relating it to slopes of tangent lines. It's like, the slope of the tangent line is this, and so the area under my tangent lines is just given by this value here. So again, it's relating area and tangent lines together in a very intimately connected way that doesn't necessarily make any sense beforehand. And if you're curious about the proof of that, just let me know and I can leave that in the percentage section down below. Last thing, and it won't take me too long before we get into the life lesson, that I want to talk about is average value, because again, average value is something that's important to some of the research that I want to present to you guys when we get there. And basically, an average value can be calculated. So if I want to calculate the average, which I just abbreviate AVG, the average value of f on the interval from A to B, well, I can calculate that average value with just 1 over b minus a. So this is the length of the interval, so 1 over the length times the area. And so what this should kind of ring a bell on is, well, like, area is of a rectangle's length times width. I just told you I divide by the length. And so what this is basically saying is that, again, this represents area, this represents lengths, and so the average values basically can be interpreted as the width of a rectangle, which makes a lot of sense. Because, let's just kind of get a picture going on here, again, of our favorite function, y equals f of x. So if I look at the average value from like here to here, well, my average value might be something like this. That's actually probably not my average value, but close enough for government work. And so notice this creates a rectangle. Here, let me maybe draw a slightly more accurate average value. So, yeah, that looks a little more accurate. Right, because the average value is, well, what does it do on average? So there should be an equal amount above it and an equal amount of the function above it and an equal amount of the function below it, right? Because then it balances out and you get the average, right? And so when I draw my average height here, that creates a rectangle, and that's basically where this idea comes from. So you can calculate the average just dividing by the length of the integral. And so that's really just kind of what I wanted to point out here. There are other uses of integrals, like I mentioned at the beginning, but we're not going to get into all of that. I'll talk about how they help us weaken the notion of a derivative in a future video, but for now, I want to get into the life lesson. So basically, like I said, the fundamental theorem here related to tangent lines and slopes, or tangent lines and areas under curves, and it's just like, how do those things go together? That doesn't make any sense, but mathematically it's like, boom, there it is. They are connected, and you're just like, whoa, weird. And I want to challenge you to think about those fundamental theorems in your life. So, for instance, think about, how a situation at work Monday morning affects what happens to you on Thursday night, how you feel. Like if you have a really tense, really frustrating conversation Monday morning, that could just affect the way you work the rest of the week if you don't resolve those feelings. If you just bottle up those feelings of frustration or anger, and you just sit on those, it's going to affect you the rest of the week, even though, that conversation Monday morning had nothing to do with why, you're fighting with your roommate about doing the dishes, then you kind of look at it and being like, why am I getting so angry about doing the dishes? It doesn't make any sense. Well, it's probably because you bottled stuff up from work Monday morning. Does that make sense? And so, like, we're very connected creatures, and so when we don't resolve those types of things, it bleeds over into the rest of our lives, positive or negative. Like, it could be a good thing, and it could just make you glow the rest of the week, and you're just like, why am I glowing right now? Well, that really awesome thing happened Saturday night or whatever. Does that make sense? And it's more than just like situations and how like situation A influences how I feel and react in situation B. It's also just like who we are. Like, it's really easy to think of our different aspects as being disjoint. So like our physical side and our mental side and our emotional side and our spiritual side, like it's really easy for us to think of those as being completely disjoint from one another. But, studies have proven over and over again that physical exercise reduces stress. Like, our taking care of ourselves physically reduces our mental stress and like how we feel emotionally. So it's like, oh, like that influences it. And it goes the other way too. Like, my mental health affects how much I want to take care of my body physically. Or like what I think about throughout the day influences how I feel. And how I feel influences what I want to think about. All these things are very, very connected within ourselves, and we don't always realize that because, again, this is something I'm a little bit passionate about, but society and culture has a tendency to put us in boxes very early on. They tend to either label us as emotional people or logical people. People who are just cold and don't do emotions at all. You're like a mathematician. Why are you feeling right now, and why are you enjoying art? That's weird. No, you're just supposed to do math. You're not supposed to enjoy art. And vice versa, like we're shoved into these boxes, and in those boxes, we have a tendency to disconnect that aspect of ourselves from the rest of ourselves. So if we're shoved into a physical box, like we're a very physically athletic person, we might disconnect our physical nature from our mind and our feelings and our spirit, and just kind of focus on that thing because that's the box we were shoved into, and we don't let our body talk to these other areas of our lives despite the fact that they're connected, that they have to talk to each other. Does that make sense? Or again, let's say you're a very emotional person. Well, sometimes, people only want to engage with you emotionally, and they don't want to engage with your intellect, and so your heart and your head might not learn how to talk to each other. Or if you're a very intellectual person, like a mathematician, this is something it took me forever to figure out how to do. Is like, how do I let my head and heart talk to each other? I was shoved into the mind box for so much of my life. Like, how do I actually get my head and my heart to talk to each other? How do I let my emotions have weight but not let them run my life? And how do I let my head have weight but not let it run my life? Does that make sense? Because we're all connected. We're living embodiments of fundamental theorems. Because, things that we don't necessarily think are connected are connected. Sorry, I got a little bit impassioned there, but I hope that idea makes sense, and I hope it, again, just encourages you to think about, like, well, how do these things that I think of as disjoint, that I tend to put in boxes and separate in my mind, how are they actually related to each other? Because chances are they actually are related to each other, just because of how we work. Cool. Well, with that being said, I want to go ahead and wrap the video up. I don't want this one to get as long as the others have been. But yeah, just let me know if you'd be interested in seeing, well, the proof of this fundamental theorem of calculus, proving that area is related to slopes of tangent lines and all that stuff. And until next time, have a good one. Bye.